Hi, Harry. Right, so I'm just going to go through the homework questions that I gave you last week, which were on pressure. We had started the chapter, the pressure gravity moments chapter. Okay, so a sheet of steel has a layer of tin electroplated onto one side. The thickness of the layer is 2 by 10 to the minus 6 meters, and 20 grams of tin is used in all. What is the area of one side of the sheet? Okay, so they give us the density, so presumably we're going to have to use density equals mass divided by volume. Sorry, it has a layer of tin electroplated onto one side of it. The thickness of the layer is that. Oh, they're looking for the area. Sorry, I thought they were looking for one of the dimensions. Okay, so the density is 7.3 by 10 to the 3. The mass is 20 grams, but we need that in kilograms, so I'm going to divide it by 1,000. So it's 0.02. And we don't know the volume. Okay, so if we bring the volume up here and then 0.02 divided by 7.3 by 10 to the 3. Yeah, that's right. So the volume is 7.3 by 10 to the 3. So I'm getting 2.74 by 10 to the minus 6, and that's going to be meters cubed. So it's going to be a rectangular piece of tin. So it's going to be length by width by height equals the volume. Yeah? So length by width is going to be our area, multiplied by the height is 2 by 10 to the minus 6. And that equals our volume, which is 2.74 by 10 to the minus 6. So I'm going to divide by 2 by 10 to the 6. Oh, sorry, minus 6 even, to cancel that, and then do that over here. So I've got that number divided by 2 by 10 to the minus 6, which is giving me a length by width, which is an area of 1.4 meters squared. That's what I'm getting. Okay, that's question 8. And then the next one is calculate the pressure on the table caused by the block if it's lying on side A, side B, and side C. Okay, so we need to do pressure. It's going to be force over area. It says the block is 4 kilos, which means the force is going to be 4 multiplied by 9.8, which is 39.2 newtons. And in the area, I'm going to do each of the areas. So the area of A, we wanted a meter squared, so it's 0.03 multiplied by 0.05. So that is, so area A is 1.5 by 10 to the minus 3 meters squared. Area B then is, what's that, 3 by 9? 3 by 9, so 0.03 multiplied by 0.09. This is 2.7 by 10 to the minus 3 meters squared. And then C is 9 by 5. So 0.09 multiplied by 0.05 is 4.5 by 10 to the minus 3. Again, meters squared. Okay, so the pressure for A is going to be pressure equals the force, which is 39.2, over the area for A, which is 1.5 by 10 to the minus 3. And that is 39.2 divided by 1.5 by 10 to the minus 3 is, so that is 26,133.3 recurring, and the unit for pressure is pascals. Okay, then for P, it's still 39.2 because it's the same one. But on B, it's got a bigger area. It's 2.7 by 10 to the minus 3. So 39.2 divided by 2.7 by 10 to the minus 3 is So bigger area, so you'd expect, you'd expect less pressure, and it is 14,518.5 pascals. And then on C is the biggest area of all, which means you'd expect the smallest pressure. So, sorry, it's very hoppy. So it's 39.2. And then the area of C is 4.5 by 10 to the minus 3. So that is 39.2 divided by 4.5 by 10 to the minus 3. And we're getting 8711.1 recurring pascals. Yeah. Okay, and then question 4, which this was pressure due to a liquid. So a rectangular block has dimensions 10 by 20 by 30. It is placed with its upper surface at a depth of 1 meter, which is in the picture. The pressure at the upper surface due to the water. Okay, so pressure due to a liquid is rho GH. Rho, it's there, is the density, so that's here. So that's 1,000. G is gravity, which is 9.8, and the height is 1, because it's at a depth of 1 meter. So that's going to be 9,800 pascals. Okay, part 2, the pressure at the lower surface. Okay, so it's all going to be the same, 1,000 by 9.8, except the height is now going to be an extra 10 centimeters, so it's 1.1. So that's going to be 10,780 pascals at the lower surface. The third one, the force on the upper surface. So pressure equals force over area, which means force is pressure times area. The pressure on the upper surface was 9.8. And the area of the upper surface, you can see it over here. So it's going to be 0.2 times 0.3, which is 0.06 in meters squared. So multiply that by 9,800 and I get 588 newtons. That's the force on the upper surface. I'm just going to put a little box around this. Right, so then part 4, the force on the lower surface. So exactly the same thing. Pressure is force over area. Force is pressure times area. The pressure, what was it, 10,780. Area is going to be the same. So that is 10,780 multiplied by 0.06. So that is 646.8 newtons. And again, that is expected because pressure increases with depth. So the water at that lower surface will exert a bigger force than the water at the upper surface because it's deeper. So the last part there you can just see is if the weight of the block is 70 newtons, determine whether the block will sink or float. Okay, so what we have is we have the weight acting this way and it's 70 newtons. The force on the upper surface due to the water, so that's that force, is going to be 588 newtons. And then the force on the lower surface due to the liquid, so that's below pushing up, is 646.8 newtons. So essentially what we have is up, we have 646.8. Down, we have 588 plus 70. So we have 658 newtons. So what's winning? Down is winning, isn't it? Yeah. So therefore, it'll sink. Okay. So that's just based on the stuff from last week. So check your answers. I haven't actually looked to see if you've emailed them to me, but check your answers And if you don't get anything, just let me know. Okay? So then what I want you to work on for this grind today is the rest of this chapter. Okay? I don't think there's a lot that's going to catch you out. So Archimedes principle you need to know. So I have a nice little version of it done out here. I just did this one. Here's one I made earlier. So Archimedes principle, the statement is that the upthrust is equal to the weight of the fluid displaced. You have to then be able to explain that like experimentally. So the way we get the upthrust is you use a Newton spring balance and you hang a weight off it. So like this here. And the Newton spring balance will tell you the weight. You can normally read it in newtons. And then what you do is you take the exact same weight and you put it into water. So the water will push up on it, which will cause the reading on the Newton balance to go down a little bit. And the difference between the two is basically the upthrust of the water. Okay, so that's how you calculate the upthrust. The weight of the fluid displaced then, this is a junior cert experiment where you use the overflow can. So you fill it up to the brim. You put the same weight into the water and that will cause a certain amount of water to spill out. And what we need to do is figure out the weight of this water. Okay, so be very careful. It's weight, which means it's in newtons. So you'll get the mass of it by literally putting it on a scales. So you put it on a mass balance and you'll get the mass of it. But that will give you the mass in kilograms. And then we need to turn that into a weight. So we do that by multiplying by 9.8. And Archimedes' principle says that those two things are the same. So whatever the difference on the Newton spring balance is, that should be the same as the weight reading on the mass balance. Now, like I said, it won't read weight. You'll have to calculate it. Yeah? Then you have the law of flotation. So the law of flotation, like in the picture, is where the object is floating. So like you push it into the liquid and it gradually works its way back up until it sort of bobs on the surface. So provided the surface is completely smooth, the wrong word, unmoving, calm, still, yeah? What you have is that the reason it stays there is because the forces are balanced. So do you remember the whole Newton's first law? It will remain at rest. Provided the forces are balanced, it will remain at rest or travelling at a constant velocity. In this case, it's remaining at rest. So these two forces are balanced, which means the upthrust provided by the water is exactly the same as the weight of the object. If the object weighed more, it would sink. Yeah? So they're exactly the same. So all that happens in the law of flotation is you take Archimedes' principle. Oh, did my C there? Sorry. So you take Archimedes' principle and you just acknowledge that the upthrust and the weight of the fluid displaced is, so that's Archimedes' principle. Sorry, hang on. So, with the law of flotation, if the object is still on the surface, still unmoving, then see here, the upward force equals the downward force. Like I said, Newton's first law. Yeah? The upward force is being provided by the upthrust and the downward force is the weight of the object. Now, from Archimedes, here, the upthrust is equal to the weight of the fluid displaced, which you can prove by doing the experiment we talked about there a second ago. So then essentially, the weight of the fluid displaced is equal to the weight of the object if the object is floating. Okay, so hopefully, again, that makes sense. And then there's a couple of things here, like a hydrometer is just like a thermometer, sort of, except instead of measuring temperature, it measures kind of density of a liquid. So depending on the density of a particular liquid, this will float at different heights in the liquid. So it might like sink really deep into one liquid. It might float very high in a different liquid. And from that, you can get a reading. It normally helps with like concentration and stuff like that. You can see here the percentage of alcohol in beers, wines or spirits is used. The density of sulfuric acid in a lead acid battery. So yeah, depending on how dense the fluid is, the hydrometer will float higher or lower. Pressure and gases in the atmosphere, so just that the atmosphere exerts a pressure. There is a demonstration for that one, which is this here, the can. So this comes up in exams, so you need to make sure you can describe this. So essentially, I don't know if I have a video of it. Essentially what you do is you take a can, normally like an empty Coke can or something like that, and you put a tiny bit of water in it. And then you heat that up. So normally using like a Bunsen burner or something like that, you heat it up until it boils. So you want the water to boil, and then you want the water to evaporate. So you'll get that happening, and you get the water evaporating. And when it does that what you are doing is you create a partial vacuum inside the vacuum. You create a partial vacuum. So when the water is boiling, because it's leaving, it's a gas, so it expands and it has an opportunity to leave, so it leaves. You're literally removing particles from inside the can. So you create a partial vacuum. It's not perfect, but it's not bad. And then what you do is you get like a big container. Do that. So it's a container of water. And you upturn the can. So you upturn the can. And what you do is you block the hole. So you trap it in such a way that the pressure inside is less than the pressure outside because of that partial vacuum. And then because of that, the pressure on the outside crushes the can, because the pressure outside is bigger than the pressure inside. And that proves that the atmosphere exerts pressure. So that's a nice demo that you need to know. And it's out there as well. Diving and pressure. So when you dive to depth underwater, because you've got the atmospheric pressure pushing down on the top of the water, and then the water, as you go deeper and deeper, the column of water increases the pressure that's acting on you as well. Like we said, pressure increases with depth. So when a diver goes to depth, the amount of nitrogen that they're dissolving in their blood is much more than it would be at normal atmospheric pressure. So if they want to return to normal atmospheric pressure, they have to do so slowly. So like for serious depths, you can have decompression chambers where the diver might increase or I suppose decrease their depth, so return to the surface, and they'd return a certain amount of the way and they'd go into decompression, and then the decompressor would basically get their body to change temperature or change the pressure they're at, but do it really, really slowly. Because if you do it really quickly, what happens is the body wants rid of the nitrogen, and it gets rid of it by bubbling the nitrogen out of your blood. And if that happens, you can get what's called a bends, and it can be fatal. It can kill divers. So, when it's like divers that are kind of, this commercial divers, people that do it for a living, they're generally put into decompression chambers, and that kind of changes the pressure very slowly and very controlled. You do have people who do free diving, so they just dive themselves. And if they do that, when they're on their return back up, they have to stop at certain intervals to allow their body to adjust to the pressure at that depth, and then very, very gradually return themselves, so that the amount of nitrogen in their blood, as the body gets back to normal pressure and it wants that nitrogen out, that it does so very slowly. Boyle's law. So pressure is inversely proportional to volume for a fixed mass of gas at a constant temperature. There is a mandatory experiment for that one, so I don't know if you did it using this fancy setup or you can just do it with a syringe. That's how I do it here, so I suppose it depends, but if you're not sure, you can ask. So we just do it with a syringe like that, and you change the amount of so you open the syringe to the max volume and connect the pressure gauge to trap a fixed mass of gas. So this would be pulled back so that you have a certain mass of gas. Oh, not that, sorry. So you have a certain mass of gas in here, and you read the volume off the scale, and you read the pressure off the pressure gauge. And then you reduce the volume, so you literally push in on that, making the volume of gas go down, and that will cause the pressure to increase. And that's all you do, just take a couple of readings. So it's nice and straightforward. The other one is very similar. It's just a more complicated piece of apparatus, but it's the same thing. You normally use like a pump, like a foot pump, to pump air in. You have your fixed mass of gas trapped up here. So you increase the pressure, and that causes this line of liquid to go up a bit. So fixed mass of gas in both cases, it's a trapped mass of gas. That's how they keep it fixed. And the other thing for Boyle's law is that it has to be at a constant temperature. So you have to make sure that when you change a reading, so if you increase the pressure on the syringe, or if you pump in extra air in here, you have to wait 20 seconds before you take a volume reading, because the friction caused by the pump causes a tiny increase in temperature, and the tiny increase the tiny increase in temperature will affect the volume of the gas. So it has to be a fixed mass of gas, which we do by trapping it, and a constant temperature, because if you change the temperature, you change the volume of the gas. So we get around that in the experiment by just waiting a couple of seconds. So that's all that stuff. This here then is Newton's universal law of gravitation. So F is equal to G m1 m2 over d squared. So the force is proportional to the masses of the object and inversely proportional to the square of the distance between them. So for that reason, this is called an inverse square law, which is if you double the distance, you're actually decreasing the force by 4. If you were to triple the distance, you would decrease the force by 9. So they are inversely proportional, which means as one goes up, the other goes down. And then because of the square, changing the distance has a really big effect on the force. So if you double the distance, the force goes down by the 2 squared. If you triple the distance, the force goes down by the 3 squared. If you quadruple the distance, the force will go down by the 4 squared, and so on. Okay, and that is an inverse square relationship. I think we talked about this before, but the gravitational force is a really, really small force, and it's only a force that's felt if at least one of the masses involved in the interaction is really large. So that's why we don't feel, or we don't actually experience, the gravitational force like between two people. Like technically it exists because the two people have a mass and they are a distance apart. So it is a force that exists, but we don't feel it because the gravitational force is so tiny. The only reason it's felt, or the only way it's felt, is if one of them, at least one of the masses involved, is really large. So that's why we feel the gravitational force between, say, me and the Earth, because the Earth's huge. But I wouldn't feel the gravitational force between me and a person standing beside me because both of our masses are just too small. So I have a couple of examples. They're very straightforward, and they're all done. I did these ones earlier. So, oh, that's another thing I should say. The mass here, the distance. Sorry. The distance is the distance between the centers of whatever the objects are. Okay, so like if you're talking about a person on the surface of the Earth, you would have to go from the center of the Earth. So you include, now, technically speaking, it's from the center of the Earth to the center of the person, but like the distance from my toes to my belly button, whether I include it or I don't include it, it's going to make absolutely no difference because I'm comparing it to the radius of the Earth. It just isn't going to play. It's not going to play. It's not going to have any impact on the calculations. So I have there, it's negligible, which means it's so small that it can be ignored. So you'll notice when I do the distance here, it is simply just the radius of the Earth. So it's just the distance from the center of the Earth to the surface of the Earth, because including the 0.5 meter between my toes and my belly button is just not going to have an impact. Okay. Now, I've included a couple of questions on that in your homework, so you can show me that you understand. Gravity and weight was the next thing. So I suppose just understanding that if you are a person on the surface of the Earth my weight is the same as the force of attraction between me and the earth. Do you know what I mean? So your weight is obviously your mass multiplied by the gravitational pull, and the force of attraction caused by gravity is going to be the exact same thing. So that's what I have here. So the weight is mass by gravity, and I'm down here now. And the force of attraction, we now know, is gm1m2 over d squared. So if you equate them, you can drop the mass of me, or the mass of the person. I'm calling it the mass of the man here. And you create this new equation. I call this the baby G, big G. So baby G, which is acceleration due to gravity, is equal to big G, which is the constant, multiplied by the mass of the earth. No, obviously it depends what if the person was on Jupiter, that would be the mass of Jupiter. And then the distance between the objects, which in this case would just be the radius of the earth. Okay, so it's just another nice formula there. And again, I've done out some examples, so read through these and make sure you understand them. I've done a few, I haven't done all of them, so just for time really, but read through them, and I'm going to give you those questions as well. And then the last thing in this chapter is the turning effect of a force. So we've talked about forces that cause things to speed up and forces that cause things to slow down, and then forces that cause things to change direction. But if you exert a force on an object that is rigid and has a fulcrum, so like a door. So if you have a door, it's a rigid body and it rotates about a fulcrum, the fulcrum being the hinges. Yeah, so it rotates about the hinges. If you exert a force on this door, like if you push the door, you will, instead of causing it to speed up or slow down, what you will cause it to do is rotate. And if that happens, what you have done is you have exerted a moment. So a moment is a force that causes a rotation. Yeah? To calculate a moment, or the size of a moment, it's the force that you exert, so literally in newtons. And then the other thing that has an impact on the moment is the distance from the fulcrum. Again, I'd imagine you're probably fine with this from applied maths, but that's why the handle on the door is here. It's far away from the fulcrum, because that gives you the biggest, the smallest amount of force will give you the biggest moment. If you try to push the door, if I put the door handle in here really close to the hinges, it's not an optimum way to open the door, because you'd have to put a huge amount of force to try and open the door. Okay? So the size of the moment is basically the force multiplied by the distance from the fulcrum. Yeah? So again, hopefully that's okay. Now we have clockwise and anti-clockwise moments. So if you turn something like a meter stick like this into I don't think I actually said the word, did I? Sorry. If you have a rigid body with a fulcrum, what you have is a lever. Okay, now if you turn a meter stick into a lever, so a meter stick is a rigid body, but it doesn't technically have a fulcrum, but you can give it a fulcrum. Okay, so in this question, it said, see about the center of the meter stick. So the center point is the fixed point, which is the fulcrum. And by giving a meter stick a fulcrum, you've turned it into a lever. Okay, then what we have are all these forces that have been added on. And then I'm imagining this point under the yellow arrow is fixed, like I've put a nail in it. And then you can see I've analysed the forces to see would they turn the meter stick clockwise or would they turn the meter stick anti-clockwise. So if we exerted this force, as in if we literally pulled down on the meter stick, given there's a nail in here, if we pull down on the meter stick, it would cause it to rotate in that direction, which is an anti-clockwise rotation. And if we want to calculate the moment, we do the force by the distance from the fulcrum. The fulcrum is now the nail, so we simply just do the 30 multiplied by the 10, or 0.10, and that gives you a 3 Newton meter moment. I figured out the clockwise and the anti-clockwise moments, and then I was able to, at this question they were asking us to figure out if the meter stick was in equilibrium. So it wasn't, because I had an overall clockwise moment, which means overall this would move clockwise. So then the very last thing here, and this is the experiment, is the conditions necessary for equilibrium. So there are 2 conditions necessary for equilibrium. Like I said up here, this wasn't an equilibrium. The 2 conditions necessary is that the upward forces have to equal the downward forces, and the clockwise moments have to equal the anti-clockwise moments. Okay, and if both of those are satisfied, then you have a meter stick in equilibrium. Okay, and again, I've done some of the examples, so look through them, and I'm going to give you a couple of questions. The very last, I've talked about a lever, but the very last thing here is a couple. So if you have a lever, so like this rigid body free to rotate about a fixed point, this is a set of handlebars. If you have 2 moments with the exact same size, but they're in opposite directions, so you can see by the arrows here that the forces are the same. They're the same distance from the fulcrum, but one is up and one is down. What you have is a couple. Yeah? And often the moment of a couple is referred to as torque. Yeah? Right. So that's that chapter. Like I said, if you go into the homework section then, I've given you a set of questions under today's date. Will you do them? Email them to me, and maybe get like your mom to send me a text when they're emailed so I can double check them. I don't know when your physics is, so I don't know if we have time to do another grind next Monday, but you can let me know. And yeah, if you have any questions when you're studying, just send them on to me. Okay? All right. Let me know if you need any more help.